Thanks, Alex. I wanted to start by just giving a special thanks to the ClojureCon organizers. When I was in high school, we had a Model UN team, and I was always really jealous that they got to go to DC, and I finally feel like I've got to live that experience. So yeah, like Alex mentioned, my name is David Pick. I'm the technical lead for Braintree's data engineering team. So we work on everything from our data warehouse solution to our search and reporting infrastructure. And a little while ago, we were trying to figure out how to best get data into that system. But before I get into that, I want to talk a little bit about Braintree. Braintree's a payments company. We try to make it as easy as possible for anybody to get money online. So whether that means somebody needs to give you their credit card number, their PayPal, Bitcoin, whatever that may be, we try to make it as easy as possible for you so you can get back to building your actual business. And while you may not have heard of us, you probably have heard of some of our clients like GitHub, Stack Overflow, Uber, Airbnb. So yeah, if you're trying to take money online, feel free to check us out. So before I get into talking about a data pipeline, I want to talk a little bit about the problems we were trying to solve and then go from there. And by far the first and one of the biggest ones we had was trying to figure out how to get more data about boy bands. We really like boy bands at Braintree. But in actuality, we use a tool called Amazon Redshift as our data warehouse. And this just happens to be the first picture you'll find on Flickr when you search for Redshift. So the problem we were running into was that keeping your data warehouse in sync with your primary databases is generally really difficult. And that tends to be because of a few reasons. The first and foremost being that deletes in your primary database when you have some sort of batch job the way Braintree gets data into our data warehouse is every few hours we spin up a job that goes and looks at our database. And because we're a Rails shop, we happen to have a created at and updated at on every table. And we can look at the updated at and say, was this row changed since the last time I ran my ETL job? And if so, give me that data and I'll ship it off to the data warehouse. And that's a big, arduous process. We generate massive CSVs and upload them to S3 and then into Redshift because that's how you get data in. And deletes are really hard to keep track of when you have that kind of job. Basically, if you go into your database and you delete a row and then your ETL job runs later, there's no indication that that delete ever actually happened. So unless you're using Datomic, it's really hard to figure that out. And that ended up being a really significant issue for us in our data warehouse because we would go and we would upload data into Redshift, and then later we would go delete it in our primary application, and it would hang out in Redshift. So our data analysts would go and say, oh, my numbers look a little funny this time I'm running my analytics, and we would have to say, well, that data's actually gone in our data warehouse, and we had no way of knowing it, so you guys kind of got screwed. Sorry. And in addition to that, while we are able to keep track of what changed using those created at and updated at columns, it's really not great to have to maintain extra columns in our database just to make our ETL jobs work. And that's not necessarily the case, but we do have some immutable tables where we were just sticking created at and updated at on them for whatever reason, just because it's the Rails default. And it's really, it's extra space that's taking up in our database, and we were starting to run into data size concerns, and so those were the first things to start going. So we had to figure out a way to continue to make our ETL process work without having any indication of what changed just by looking at a specific table in our database. And then along with that, those batch updates that I was talking about that work while we have created at and updated at are really slow. And totally dependent on how much data you've inserted since the last time you ran. So you'll have no idea how long they'll take unless you go do some analysis about how much data you've inserted into your database since the last time you ran your ETL job. So a lot of times we would have analysts who would come to us and say, people are asking us to give us numbers about, the last day's transactions that we processed. And we'll have to say, well, we did a lot of traffic yesterday, so it's going to take 6 more hours than we thought it was to get all our data up into Redshift. And so, sorry, they're going to have to wait for their data, it's not a great situation to be in. And so this, figuring out the best way to get data into our data warehouse and keep it in perfect sync with our primary databases ended up being a pretty significant concern for us. And in addition to our data warehouse, the other tool that my team is responsible for is our search and reporting infrastructure. So if you're a Braintree merchant, you've probably seen this screen if you've ever logged into our control panel. But basically what this lets you do is run a search over all of your data that you've ever had with Braintree. So this is all of your transaction data. And if you've been a merchant with Braintree, you've probably got a lot of data. If you've been there 6 or 7 years, this is every transaction you've ever run. And we allow you to facet on a fair number of things. You can click a bunch of different checkboxes. The drop down down there is for, I think, 15 or 20 different text fields. So you can say customer name, customer address, stuff, anything like that. We'll do partial matches for search. And you can do any search over any date range. And while that's a really attractive prospect for merchants, the system we first implemented when Braintree was really small and worked was entirely powered by SQL. So you would click all those checkboxes, fill out some text fields, and we would generate a really massive SQL blob and run that against our primary database. And that turns out is not really fast. It's really slow. To get even somewhat medium-sized data sets will take 30 or 40 seconds. Your search will just spin there for a while. And we actually don't have any way of asynchronously processing that. We didn't. So we didn't have a way for you to run a search and then us to run it in the background and just sort of let you know when your search was ready for you to go get data. And so any search you ran had to finish in the 50 seconds we let a request run before we time it out. So in order to combat that, to make sure that the data would always be able to be returned to the client when somebody ran a search like this, we actually just applied an arbitrary limit to our searches. So you can only get back a limited set of data. So if you're a small merchant, this is somewhat okay. It usually works. If you're a big merchant, your requests probably start timing out, and you call our support team and say, what do I do now? And our support team says, well, you should probably limit the scope of your search. So if you're trying to get all your data for a month, we say run 4 searches, 1 for each week of the month. And the bigger you get, the smaller your search range has to get. And that's not great to tell a merchant when they're trying to get their financial data. It's really not what we want to do. It's not the kind of interface we like to provide to our systems. So we knew that this was a really big problem that we needed to fix. Water here. So as we were talking about this, we were sitting down and somebody said, wouldn't it be awesome if we could just tap into Postgres's changelog that it uses for replication and then use that data to go into any one of our external systems? And that ends up being a really powerful concept because what you're doing is you're essentially creating what you would do in this situation is you could essentially create materialized views that normally would live in your database and be forced to continue to be in Postgres, but take your data, get it out of your database, and generate a materialized view in another system. So Redshift and Elasticsearch now just become materialized views on top of your database that are always up to date. And while we were thinking about this system, thinking, oh, this would be really cool, we realized that pretty much all of our external dependencies go down. Turns out Redshift goes down probably every other day. Amazon will just restart your instance without telling you. Sometimes one of your nodes, like the machine dies, as machines are apt to do. And Redshift goes away for a while, and eventually it comes back with all of your data. But it's probably pretty slow for a little while, or it just stops accepting requests entirely. And so we knew that our system had to be resilient to that. If a change came through our question marks, it had to sit there until Redshift or Elasticsearch was ready to accept it. Elasticsearch has very similar issues. We know from Afer's talk it's not the most reliable system, so we didn't want to treat Elasticsearch as a primary source of truth database. We didn't want to assume that once data was there, it was going to stay there. And if the cluster split brain that writes were going to end up in the right place. So we knew that we had to be able to allow for downtime of these backend services, and that in the event of downtime of these backend services, we were able to get our data continue to hold on to that data and not cause issues in the database. And in addition to that, we knew that if this backend system, this intermediary messaging system, were to go down, We also don't want to cause issues for our primary database, because the worst thing we can ever do is have our data warehouse cause issues for our primary database and make it so that our merchants can't accept transactions. We want to continue accepting transactions no matter, like in the event of catastrophic failure, we should always try to keep continuing to accept transactions, because if we don't, our merchants can't get money from their customers, and that's not great. It's really not a great situation to be in. So we were talking about this one day, and I was talking to another guy on my team named Dave. Turns out that Dave's at Braintree really like data engineering. I don't know why, it might be the alliteration, but there's 3 of us on a team of 5. And he goes, well, we can't really tap into the Postgres changelog that it uses for replication. It's not something you can do until another few Postgres versions, and we won't be there for years. But there is this thing that we've used before called Londis replication. And Londis is a trigger-based replication system that's built on top of a PGQ, which stands for Postgres queue. And PGQ was designed to basically do what we want, asynchronous processing of live transactions. So basically, you can, at commit time for a transaction, you can run some arbitrary code and insert an event into a queue in your database. And so what we did is we wrote a database trigger, which is the same way Londis works, that fires on every insert, update, or delete. And when that trigger fires, it inserts what changed into this queue, and we can consume that on the back end and use that to power our external systems. And that gets us some really cool benefits. You get the same ACID semantics you get with Postgres. So if your transaction doesn't commit, your insert into PGQ doesn't happen either. And in addition to that, it's extremely fast. We know that our Rails applications all have a persistent connection to our database, and it's going to be fast. Because if it's not fast, we have bigger problems than just our backend system. Our Rails application is going to have issues, and we monitor that extremely closely. So that's really beneficial from us, because we don't want to make creating a transaction take any more time than it would have before for any external dependency. Cool. So our system looks a little bit like this now. We're running PGQ inside of the database, and something's there consuming it and writing to Redshift and Elasticsearch and maybe any other system that we have. But we still actually have an issue that we talked about before. And that's what happens when one of those backend systems goes down, like they're apt to do. So if Elasticsearch goes down, PGQ actually only persists those events for about for an hour and a half. And that's because, like I said before, PGQ is designed to make itself fail before causing failures in the database. So if the data size grows too big in PGQ, it'll just start throwing messages out after either a certain amount of time or after every consumer has seen those messages. So we don't end up filling up disk on our database box. And so that means if Redshift goes down for an hour, we start to lose messages. And that's been known to happen. So in the middle of the night generally, Redshift's generally pretty good in the day. But we don't want to take that chance. An hour really isn't that long. If something goes wrong, maybe the code that's consuming PGQ and writing to those systems has issues and we need to figure it out. An hour really isn't that long. And we need to figure out exactly what's going on and make sure we still don't lose those events. So we were talking about this, and it turns out there's another system that had some pretty attractive properties for us. And that was Apache's Kafka. And if you guys ever try to find a picture of Kafka for a presentation, it turns out it's really difficult to find one that isn't disturbing. So this is the best I could come up with. But Kafka is a pub subsystem. It works from the outside. It looks like it works basically like every other pub subsystem you've ever seen. You have producers, you have consumers, and there's a Kafka cluster with multiple nodes. If one node goes down, you don't lose any data. It fails over to another node, things are okay. And then there's topics inside of the cluster. So it's basically like every other pub subsystem you have with probably less stuff. It doesn't keep track of who saw a message. It doesn't keep track of acts or writes. Kafka takes messages, and then your consumer can get them out by saying, give me a message at a specific offset. And the way Kafka topics work is that they're actually split up into different partitions. And you determine what partition you want to write a key to when you write to that topic. And the benefit of those partitions is that every partition is guaranteed to be on a single machine. And the ordering guarantees that Kafka provides is that if you insert a message into a single partition, it's always going to come out in the same order you inserted. But if you're reading from a single topic, it is not guaranteed that you'll get messages out in the correct order. You may get messages from partition 1 before partition 0, despite partition 0 having written first. So that ends up being really important later. But the other important thing to know about Kafka is that these topics, because they're just raw data, we're not trying to keep track of acts or anything, any sort of that metadata, they get immediately written to disk and kept for however long you want. So what you can do with Kafka is you can say, I want to keep my data for a month. So every message you write to Kafka will stay there until it's been there for a month, and then it'll fall off the back end. And you can specify how long you want to keep data yourself. And so what you get is a mutable record. It's not really immutable because stuff falls off the back end, but you get this record of everything you've done in Kafka for the past month, the past year, however much disk space you have. And it's actually designed to run on spinning disks, so it's really good. If you say, give me message 6, it will pull the next messages in the partition into cache. So you can get that stuff out really fast. We've seen speeds of 250,000, 300,000 messages a second going out of Kafka. So it's actually really good at dealing with spinning disks and getting data out. So you can have a lot of storage. So we stored data for a week. Just because we picked it arbitrarily, we can actually store data for significantly longer than that. But that means that if one of our backend systems goes down or our processing code goes down, we can actually just rewind our Kafka stream. And so the way that works is it's the job of the consumer to tell Kafka which message it wants. So consumer 2 will say, hey, I've been consuming, and all of a sudden I realize Elasticsearch has been down for the last hour or whatever, half an hour would be really bad for us, last 10 minutes, but I've consumed messages up through message 11, and I need to go back an hour in my data. So I can, as consumer 2, I can actually just say, Kafka, give me messages starting at message 3 again, and rewind my stream and replay it back into my external system. And that ends up being a really powerful concept because it means that not only can any of our backend systems go down, our processing code can go down, and our queuing code in the database can actually, we can stop reading it for a little while and then start reading it again, and we still won't lose any data. So before I get a little bit further, I want to talk a little bit about how we're using Kafka to do these types of things. And in Braintree's architecture, our primary database is sharded. So each one of these is different shards, like the 0, 1, 2, and 3 are different shards in our infrastructure. And we have a partition on 2 topics for each one of our shards. We have a data stream and an event stream. So the data stream is basically populated by that database trigger I was talking about before. And by inserting every event from a single shard into a single partition, we can guarantee that the messages for a single database are coming out in the same order they were inserted. So we still get those transactional semantics coming through Kafka. And what we realized is that having a raw stream of the database is really useful. But it's actually also really useful to publish domain events to a pub subsystem and have other consumers consume them. So we do something very similar with what we call the event stream, which is just another topic in Kafka that can be written to directly from Rails. And that has turned out to be really useful for other consumers of Kafka in our infrastructure. We have other applications that consume transaction created, transaction settled type messages from our gateway and then do stuff with them. And actually, the first time somebody consumed that, they configured the backend system incorrectly. So the very first day we had this system in place, we read a bunch of messages out of Kafka. The backend system was configured incorrectly. The messages were thrown on the floor. And they realized it, and 10 minutes later, they fixed the configuration, rewound the stream, and replayed those events into their system. And it wasn't a really big issue. They didn't have to write a bunch of custom code to go figure out what did we miss, what's in the database, how do I generate these messages again. It's all just sitting there in Kafka and will be there for a significant period of time. Cool. So I've been talking for a little while now, and it turns out we're at a Clojure conference, and I haven't mentioned Clojure yet. And our system looks kind of like this. We have PGQ, we have Kafka, we have Redshift, we have Elasticsearch. We know we need to get data between all of them, but we haven't really figured out how yet. And so we were thinking about different options. And as a Ruby Rails shop, it probably would have made sense to go with, like, your first thought would be that we would just do Ruby. But what it turns out, that's not what we did. We went with Clojure. That's kind of dark, but that's OK. So yeah, like I was saying, why would we go with Clojure? Given that we're a Ruby shop, pretty much every one of our other applications is written in Ruby. It doesn't really make a lot of sense. And it turns out that there's a couple of benefits of going with Clojure that you just can't do in Ruby, like, as most of you probably know. Being on the JVM is really useful for us because a bunch of these systems that we're now dealing with are JVM based. So we have Kafka, we have Zookeeper, which is used to manage Kafka failovers, we have Elasticsearch. These are all JVM based services. And being able to use the JVM clients that are published by these, these tools is really useful. If you're not using the JVM-based client for Kafka, you don't get a bunch of really nice features because nobody else has taken the time to implement them. And you tend to lag behind the Kafka releases. So if Kafka 8.3 comes out tomorrow, the Java client is guaranteed to have all the same features, to have feature parity. But using the Ruby client, we'd be way behind until whoever was maintaining the Ruby client decided to upgrade it. And that's not really where we want to be. We want to always have the client library with the best semantics for dealing with the tool that we're using. In addition to that, we are also processing a lot of different topics. And inside of those topics, we're processing a lot of different partitions. So we have a lot of stuff going on concurrently in the system. And if anybody has used Ruby, you know Ruby's not really great at concurrency. So we thought about running a different Ruby process to consume every single one of our partitions and every one of our topics. But it turns out that that's really a pain to manage. And then you can't really communicate between those Ruby processes unless you use an external database, something like Redis or whatever you were using. And that's just another added dependency that you don't really need. There's no point in having it here. And the third thing that we liked Clojure for were the abstractions it provided. So to go through those, I'm going to start going through those now. The first one was just infinite sequences. It turns out that when you're dealing with a data pipeline, it's just a really big infinite sequence that's coming from an external database. So the Kafka client says, generate me a consumer, call this messages function, which is just going to return an infinite sequence that will block when there's no new messages. And that provides a really awesome semantic for dealing with your external, for Kafka. And we ended up implementing something very similar for PGQ, where you can just say, PGQ, here's a queue, give me all my messages in an infinite sequence, and I'm going to process them. And so from an application standpoint, that's really great. You don't have to think about the logic for dealing with your queuing system while you're trying to figure out the domain logic for processing messages. And your code ends up a lot cleaner. It's all abstracted away into this infinite sequence. And in addition to that, something we are very aware of and we're very aware of testing. Braintree has a strong culture of testing. We do TDD, all the usual things you would expect from a Rails company. So testing is really important to us, and we didn't want to change that while we were working in Clojure. But when your infinite sequence will block when there's no messages on Kafka, you can end up into some weird situations where your tests just hang. So say you have a bug in your code and you write 2 messages to Kafka and you were expecting to write 3, and then your test tries to read off 3 messages and do some assertions on them. Well, your test now just hangs waiting for the next message to come through. And it turns out that in the beginning that happened to us a lot. So the first thing we did was split apart the code that dealt with handling messages and the code that dealt with talking to Kafka. So we have that infinite sequence, and here in this process messages function, we can either pass in an infinite sequence, or in our tests, we can just pass in a finite sequence and do some assertions on it. And what that means is our tests actually complete even when we have a bug. We get some reasonable output that allow us to help debug our code, and we can figure out what's going on, instead of just our test hanging and having to Control-C it and going, well, the bug could be anywhere in our code base. We got to go figure out what happened now, which is, it's really not a great situation to be in. I'm going to stop closing this. So moving on, the concurrency mechanisms provided in Clojure are generally pretty great. But if you're not using core async, you want to start with something in the core of the library. Our first stab at it was something like this. And when we started this, we actually had 3 Kafka topics for Elasticsearch. So we would break apart the data stream into just the data we needed. There were like a merchants create, a transactions delete, and a transaction insert, which actually had inserts and updates. And we just stuck those in threads and said, well, this is good enough. We're going to be processing forever. We want this function to continue running forever. And we'll just run these threads, and things will be great. And they worked out pretty well until the first time we sent a message with data we weren't expecting. And the code threw an error, and our thread died. And it turns out if you have a bunch of threads and one thread dies and the other ones keep running, that thread is just not running anymore. So you can run some try catches, do that kind of stuff, but really you kind of want to log that error. You want to know that that message didn't make it through, and you want to do something about it. And so it turns out that the error handling when you just use raw threads leaves something to be desired. So the next thing we did, and I should preface this by saying none of us were Clojure experts. I was the only one who had any Clojure experience going into this project, and it was mainly, it was not a lot. It was not significant experience. Nobody else on my team had worked with Clojure before this. So we pretty much tried everything. So the next thing we tried was using agents. We were like, oh, agents are part of the core language. They provide a better abstraction on top of threads, and they have built-in error handling. That's exactly what we need. So we can, we capture an error, we have some logic to deal with the error. Either we send an email to the team, we throw an Nagios alert, do whatever. And then we just continue with our thread and continue processing messages, because chances are that one message had issues and stuff is okay. And this is pretty good, but it's really not what agents are intended for. We ran into some very strange issues where that mutable, we didn't actually pass any state into the agent because we didn't really care about what they returned. Everything was talking to external systems and writing data around a bunch of places. But we ended up with some really weird errors where one agent would die and another agent would get that exception inside of it. And we were having a bunch of issues with that. And in addition to that, it turned out that we wanted to talk between these agents. We had agents for doing a bunch of different things, and in each one you had to keep track of messages for different merchants and doing a bunch of different things. And agents just really weren't the right abstraction. They're not meant to process forever, and basically just didn't work for this process. So logically, the next thing we tried was core async. And what ended up being really powerful for us was having a single Go routine per merchant. And what that means is that we would have a thread reading off of Kafka that would write to a channel. So you had threads for anything that did I/O, a single Go routine for each merchant, and each Go routine, it was that Go routine's responsibility for handling all the messages for a merchant. So our architecture looked a little bit something like this. And this works pretty well. What this allowed us to do, and really one of the big issues we had was that we also wanted to have the idea of being able to reload data in Elasticsearch or in Redshift If Elasticsearch got out of sync and we were suddenly missing a message for a merchant, and we didn't notice it in the time window Kafka had, we wanted to have the ability to say, give me all of this data for a merchant again and send it through. And what you have to do when you do that is while you're sending all that old data through, if any new data comes in through the data pipeline for that merchant, you need to hold on to it and wait to apply it to Elasticsearch until all your other data has been written. So what we were able to do was just create 2 new Kafka topics, data stream reload, event stream reload. We would send all those messages through, and then in the merchant go routine, we could say, let's favor any data coming off of the reload topic. We'll process all of it until it's gone, and then we'll just have queued anything that came in on the real-time channels, and then we'll flush those out and just continue processing as normal once we're done with our reload. And that worked for a time, but there's actually some issues with this model for us. And it turns out that we don't like losing data. If we were to shut down the system because we wanted to deploy new code and then start it back up, we need to have a mechanism for saying when, saying when every message that's currently in memory has been processed. And so it turns out you can do this with core async. You can close a channel. You can continue to process. You have to do this sort of top-down approach to let's turn off our threads that are reading messages, figure out when they're done reading messages, go into our distributor, close all the, figure out when it's done reading messages, then do the same for our merchants and same for our writer to Elasticsearch. And keeping track of that shutdown logic and having no way of guaranteeing that every message in a channel has been processed was really difficult for us. And so we grappled with this problem for a while. And in addition to that, we actually had some race conditions in our infrastructure because we had no way of knowing once an Elasticsearch, something writing to Elasticsearch was done without creating basically a callback to one of our merchant go routines to say, yeah, I'm done processing all of my reload messages, start sending the real-time messages again. Because we actually have to write to Elasticsearch in 2 different ways. For a reload, we do a bulk load into Elasticsearch. For a real-time, we do single writes. So we ended up with a bunch of race conditions and a bunch of messages going between channels, which were essentially like callbacks, like, yeah, I'm done with this thing, and you can keep going. So we grappled with this problem for a while. And what we figured out was that regular threads weren't enough, agents really aren't enough, and core async can do what we want, but it doesn't really provide the semantics we want. And so we looked around, and we started thinking about this problem. And it turns out that Elixir and Erlang are really popular in Braintree right now. So everybody's like, oh, actors have semantics for that. You should look at actors. So we did. And actors ended up being a really good fit for this problem. And some of the reasons for that were that shutdown logic is inherently built into actors. You can say shut down an actor, it will process its inbox and then go away and let you know when it's done shutting down. So we can do that top-down approach really easily. We can just say shut down to our Kafka readers, then shut down to our distributor, then shut down to our merchant threads, and then everything is hunky-dory. We know we've processed all of our messages. We haven't pulled any more messages off of Kafka. We can do our deploy and start our system back up, and we won't have lost any data. In addition to that, actors kept the same semantics that Go routines and core async help for us. So we still have an actor for every merchant with a single inbox that deals with all of the messages for that merchant, which means that our code to reason about how to handle data for all of our data, you can think about just a single merchant at a time, which is a lot easier to understand. And the other thing is that it allowed us to put back pressure on Kafka. It turns out that you can't write 300,000 messages a second to Elasticsearch, but you can read off that fast from Kafka. And when you read off, 1 million, 2 million messages into memory, and you're trying to write to Elasticsearch, your GC times go through the roof. So what we ended up doing was for our reload topic, we could say, do this as a synchronous write. So we're going to read off however many, 10,000 messages, send it through our entire system, write it to Elasticsearch, and make sure that's synchronous, while at the same time continuing to pull every real-time message into memory because we don't get those fast enough, and continue to write them. So we had those different semantics. And core async can do something similar with limits of channel sizes, but that's a really big benefit for us because we can continue to use Kafka as a queue instead of just like messages funneling through it as fast as possible. And like I said, we also the actors help to avoid those race conditions because we can do that synchronous call to something that's writing to an Elasticsearch and say, don't block my go routine or block my actor until this thing that you're writing to Elasticsearch is done, and I know it's done, and then I can switch back over to processing my real-time messages so that everything flows into Elasticsearch in the correct order. And in order to do that, we used a library called Pulsar, which is the Clojure version. It's actually a Java library called Quasar with Clojure bindings that provided these semantics for us. So now our infrastructure looks a little bit like this. We've got PGQ in the database. We've got a Clojure reader in between that, writing to Kafka, and then a bunch of different processes reading off of Kafka and writing to our external systems. So a few lessons learned. GC is the enemy when you're dealing with Java projects. It doesn't matter if it's your Clojure project, if it's your Elasticsearch instance, your Kafka instance. GC is going to kill you. So try to minimize your GC pause times. We cared much more, we didn't care that much about throughput, we cared about sustained writes so that we could have a guaranteed amount of time a message would take coming from our primary database into our search cluster. So minimizing GC pause times was really important for us. And it turns out that in Clojure, you want to use a much smaller heap size than you would expect. And that helps minimize your pause times. Rich has talked about this a few times. That a smaller heap size counterintuitively will help you because you have a bunch of short-lived objects in Clojure, so you don't have to scan as much data. And then in addition to that, using the G1 GC provided significant benefits for us. It's a much more modern GC that isn't the default but comes with Java. You can turn that on fairly easily. The other thing that we realized is that monitoring our systems is really important. And Java provides great tools for this. So we use JMX for pretty much everything. We get JMX stats about how long our GC is taking. We actually have published JMX stats for every one of our individual actors. So if our system is having issues and say some single merchant's data doesn't end up in Elasticsearch, we can live query our application and say, what's going on with this merchant's actor? Is all of its data queuing in memory and something happened? Is it dead? We can get insight into that really easily. And that ends up being really beneficial for us. It's not like a black box that's just running. And we don't have to totally rely on logs. We can actually inspect the running system. The other thing to note is that you really don't want to use the default configs for any of these distributed systems. So the Elasticsearch default configs, it split brains probably every 10 minutes if you run it in a multi-tenant system. And it's just not great. And it turns out that they do this because they want you to be able to get a running instance as quickly as possible on a single machine. So the configs are all optimized for running on a single machine and not in a cluster the way they were intended to be. So don't trust the default configs, read through everything, understand the system, and go from there. And just use an abstraction model that helps you to avoid race conditions. So by creating those, having the ability to do synchronous and non-synchronous calls is really beneficial. Keep track of that. And just a couple of future uses for this kind of system is really any materialized view of your database. So if you have a cache system and all of your code for updating your cache system is in your application logic, it kind of pollutes your application logic and it's really difficult to keep track of. But when you can have an external system that just listens to your database changelog, your cache can always be up to date and you don't even have to think about it in your application. You can go straight to the cache. Which is really useful and makes your application code a lot simpler. Just some other uses. We can now do a lot of different real-time events. So our data scientists are really interested in doing real-time fraud monitoring based on this. Right now, we're always like a few hours behind with our fraud models because they have to wait until data has moved into other systems. So they can actually just consume Kafka themselves without causing any issue to our primary application and do these kinds of do basically anything they want to. One of the other interesting things I've been exploring is report generation. So we generate some pretty massive reports for our merchants, especially our really big merchants. And if you can consume a data stream or an event stream and build up your reports iteratively, you can actually just cut it at the end of the month and email it to the merchant. There's no big query that has to run on your database. There's no data intensive anything that has to happen. It all happens in real time and just sort of builds up. And you can break it down as much as you want, send pieces, and send your customers whatever. And basically any async data processing that you have that wants real-time events from any system ends up working really well in this scheme. So thanks for coming. I'm at David Pick on Twitter if you want to see pictures of food I make. Other than that, you probably shouldn't follow me. Any questions? They're separate JVMs.
Why did you use Kafka? Why don't AWS?
We don't run in AWS. We run in our own data center, and the latency talking to AWS would have been terrible. We can't afford to have that much latency. So.
Did you try to solve any authentication authorization with Kafka, or is it just open?
For security or for our application? No, our entire data center is a PCI zone, so we assume that if you made it into our data center, you have made it past all of our security measures and you're okay. Yeah.
For the problem that you used Quasar and before that used co-racing, did you even consider using thread pool executors and overriding that using poison pills to kill the threads without losing any data? These things are already JVM and people are using it a lot instead of dropping back to Erlang or Quasar.
So we're not using Erlang. Quasar is written in Java. We didn't actually consider those. We are not Java experts, so we sort of searched around for a solution, and that's what we came across and worked for us. So we didn't consider those.
Have you had an outage of Kafka that lasted for more than an hour, and did you lose data in that case?
We have not had an outage of Kafka for more than an hour. We have had Kafka outages where data queued in Postgres, but we were able to bring it back before that happened. Yeah. Anybody else? Cool. Thanks for coming. Yeah.